I was behind on emails. Apparently I can't do a test today, so it's just been pushed to the next class. I didn't realize that at the time of class. So I tried to update everything on My Notre Dame on that end. But if you didn't see that, or if you weren't sure, my apologies there. Why is it? Everything is plugged in. This thing is plugged into here. So my plan for today is going Why are you not finding this thing? Ay, 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 ay. All right, if this doesn't work one more time, we're going to go back to doing this the old-fashioned way. All right, well, I have no patience for this right now. Oh. All right. What I'd like to do is I'd like to spend a little bit of time here at the start just doing some like basic review stuff for the test, and then we'll talk a little bit about the next section. Sound okay with everybody? So I've cooked up just like, I don't know, like a half dozen or so little questions here to look at. So why don't you guys scrap sheet of paper, whatever, take something out, and give you a few minutes on each of these to kind of think through things, and we'll go through it together and talk about the approach that you'd want to take for this or what we'd need to check. But I think this is a nice little kind of, quickie review of some of the big ideas. So the first problem here, we just ask which one of these is differentiable. You're given three pretty similar looking piecewise functions. So take a minute, kind of think on that, play around with it a little bit. I'll stop talking, let you do that in a few minutes. We'll talk through the way you'd want to approach something like this, or how you check for differentiability. I'm looking around, I'm not seeing a lot of progress being made, so I'm just going to start. Is that okay? When we say something is differentiable, what does that mean? The derivative exists. What does that mean, though? Like from a practical standpoint. Like how would you use that? How would you want to test for that or check for that? Okay, so that's a good point, but we need to get to that like before we jump to that point. But you're right on, Peyton. We do need continuity is going to become important here. But let's talk about what we mean by checking differentiability. Yeah, I think you're on the right track, but I think I want to take a couple steps back from that even before we get to there, David. But you're right on. Lucas?
Well, I was just going to say that when you plug in x, the derivative spits out the same answer.
It spits out a number, right? Yes, that's what we mean by differentiability. So like, can I take an x, plug it into the derivative, and have it spit back out a number to me, right? A finite value. Everybody's okay with that? So not undefined, not positive or negative infinity, a finite value. So if I look at this piecewise function is composed of two polynomial parts, right? The derivative of a polynomial is just going to be another polynomial, right? And the domain for a polynomial is all real numbers. So the only place that I could lose my differentiability on this is where the two pieces of my piecewise function meet together. So the only place I care about is at x equals 1. Is everybody good with that reasoning? Okay. So I'm going to circle back to Peyton here now because she had a great point. We've seen that differentiability can kind of go away in 4 specific situations, right? Those 4 specific situations are a discontinuity, which was Peyton was saying we need to make sure we check continuity. What's the other 3? Okay, a sharp corner, absolutely. Yep, we'll need to check for that. A vertical tangent is what you're saying. And the other is if you have like a closed interval, right? Like a square root function has a domain where the closed interval where it starts at a single point. So those are the 4 things that we'd have to worry about. Now, for a polynomial, can you have a vertical tangent? No. Really, the only place that you'd have to worry about that is in like a cube root kind of situation. That's your canonical example. Now, since it's piecewise, can I have a corner? Yes, right? Because if the 2 pieces are fitting together, you could certainly have a corner. Now can you have a corner for a polynomial? No, but if the 2 pieces, if you have 2 polynomials hooked together, that could certainly make a corner. Everybody's cool so far? Okay, so in order of the things that I'd want to check, I would want to do the continuity first. Let's make sure that these are continuous, because if they're not continuous, they're not going to be differentiable. If I look at A, is that continuous? No. How did you check? Plugged in 1 at the left and right pieces, and you get 1 and 2 respectively. So they're not lining up. You have a jump discontinuity there, right? So this one, not continuous, and therefore we know it's not differentiable. Everybody's good? Okay, let's check the next one. Is the next one continuous? Yes, again, we plug it in. We get 2 for each piece when we plug 1 into each piece. Is everybody good with? I can just say that what we're doing for the continuity check, the numbers are so easy, it should be no problem. Okay, so this is continuous. That doesn't tell us it's differentiable, though. It just tells us that there's not a reason that it's not differentiable. That alone is not enough of a check. Let's check the other one. Is that continuous? Yes, right? When I plug 1 into both pieces, we get 2 again, respectively, right? Okay. Now what we want to check for is the corner, right? That's the other piece that's possible in this situation to cause differentiability to go away, right? Because we can't have a vertical tangent because the pieces we have are polynomials. And we can't have like a closed interval because my domain is all real numbers for these. Is everybody good with why I only have to worry about the corner now? All right. So to do that, I'm going to find the derivative of the piecewise function. How do I find the derivative of a piecewise function? Just the derivative of the pieces, right? So I have 2x plus 1 and then 2. Now notice that I didn't include the or equal to because I don't know if differentiability exists at that point. I'm good with differentiability everywhere except at x equals 1. Everybody's okay with that? So what is the slope of the left-hand piece? 3, right? Because if I plug in 1 to the first piece of my piecewise function, 2 times 1 plus 1 is 3. So the slope heading into 1 from the left is 3. What's the slope heading in from the right? 2. Do those match? No. What does that mean? I have a corner, right? That's what that means. Is everybody okay? So it basically looks exactly like the continuity check. I'm just using the derivative to do it. Does that feel good? Yes. Uh-huh. Yes. Because the graph of this thing looks like that. Yes. Yes. So that's the issue, right? Like, again, I picked these specifically because, like, one of it, like, matches one part, the other matches the other part, but not, like, neither of these first two match both, right? So if you didn't check both continuity and the corner, you're going to miss that, right? You have to check both, right? Because you can have a discontinuity, but no corner, and you can have continuity, but a corner. And if you guess what's going to happen on the last one, what's going to happen here? You'd have neither, right? Because I say which one is differentiable, that certainly implies that one of them is, and if I do that same corner check, my left-hand slope is 2, and the right-hand slope is 2, so that is now differentiable. So that's what I'm checking, okay? Does that feel okay there? Did this help kind of clarify differentiability a little bit? I think that as an exercise is really helpful in like seeing, okay, what do I actually have to do to check for this? And the piecewise ones are the ones where it's hardest to see, right? If it's a graph, I can look at the graph and I can look for visually, corners or discontinuities or vertical tangents or like a closed interval piece. All of that's easy to check for. When I have a piecewise function, oh boy, it's a little bit trickier, right? All right. So if we say a function is differentiable, what else can we say about f? So what are some equivalent statements or additional statements I can make here? Okay, good. And symbolically, what does that mean? What's the definition for continuity? The left-hand limit equals the right-hand limit equals the function evaluated at that value, right? Everybody's okay there? What does this mean? The left-hand limit equals the right-hand limit. The limit exists. So we could also write that the limit as x approaches a of f of x exists for all a, right? Everybody's okay with that? Okay. What else can we say? This is good so far though, guys, right? Again, I just want to like reconnect symbolically and with words what these things mean, right? That helps, I think, a lot, reinforcing. So what does it mean to be differentiable again? Yeah, when you plug an x value into the derivative, and that specific value comes out, which means that the derivative exists, right? What's the limit definition of a derivative? What does that look like? The limit as h approaches 0 of f of x plus h minus f of x over h exists, right? Or there's another version of this, right? What was the other limit definition look like? And it was like the limit as x approaches a of f of x plus a minus f of a all over x minus a or something like that, right? So far, so good. So all that has to have, you have to get all of that kind of stuff if we know we have differentiability, right? So if that's a given to you in a problem, you could say any of these things, right? So if there's some algebra thing you might have to solve, you might use one of these to kind of start building out a formula of like what to plug things into. Does that make sense? Why don't you guys take a second or a minute here and try this. So it says if k of x is equal to f of x times g of x times h of x, what is k prime of 2 if f of 2 is 1, f prime of 2 is negative 1, g of 2 is 3, g prime of 2 is 1, h of 2 is negative 2, and h prime of 2 is positive 2. All right, should we start talking about this? Okay, to do the derivative of k of x, that's probably what we want to start by doing. How do we do that? What's that? Product rule. How many product rules are we going to end up having to use? 2, right? Because how many multiplication symbols are in this problem? 2. And is there any way to combine these? F of x and g of x and h of x? No, because they're just given as arbitrary functions, right? Okay. The tricky part is we have to kind of do this one at a time. So when I apply the first product rule, we have that, right? Is everybody okay with how I wrote that? Then my second product rule is going to come when I do that derivative. Does everybody see it? If you don't, speak up and we can elaborate some more. I'm trying to be pretty specific. And then what's the derivative of f of x? We just do f prime of x, right? I mean, when we plug 2 in, the derivative is -1. But like, it's not a constant, right? We're just told that limited information about it. We'll just write as f prime for now, though, right? Is everybody cool? So similarly for h of x, the derivative is h prime of x, and for g of x, the derivative is g prime of x. So I'm just going to go ahead and distribute through and take those derivatives. So we're there. Any question as how I got this far? What do you notice the pattern is with these 3 things multiplied together when I did the product rule? Yeah, it's the same 3 things, it's just the derivative's on a different function in each of the three things, right? You guys see that? Peyton.
Could you just do the product rule with f of x and then g of x, and then take that and do the product rule of what you just got with h of x? You know what I mean? Like do two together and then take that result and multiply it. Okay.
Yeah, I think what you're describing is okay. I think you'd get the same thing. Right, you're just talking about grouping it this way instead. Yeah, the grouping shouldn't matter. Yep, is that what you were starting to do and just kind of, it's like, I'm not going to finish this if I'm not sure. Yeah, fair enough. And then from here, we're just plugging in values, right? I think I put everything in the right place there. And then it just like grinds some number crunch, right? Which again, this should be totally within our capabilities of doing, even no calculator. Whole number, multiplication and addition, I hopes, right? No big deal. Especially when it's single digit multiplication. Questions on what we did for that one? David? If you knew that was the pattern of what you're going to get, yes. Now, given where you guys are at, I don't know that that would have been obvious that that was going to be the result. But having done it now, and you know what's going to happen, in the future, could you treat this as like a generalization of the product rule? Yeah, for sure. Is that what you're asking?
Yeah.
Okay.
I just have
You guessed it right. That's awesome. Anthony? Nope, you'd have four terms. One function is different, a different function differentiated in each of the four terms. Yep, look exactly the same. In general, will be the pattern for, like infinite product of different functions will give you the same thing. Is that cool? Again, I feel like worth doing it because it forces you to do two rules in one problem, and then what you're left with is, oh, this is like a generalization of the rule that we had before, which is super nice. Can I take that and use it in perpetuity from here on, now that we've done it? Yeah. All right, and then my last is just some just general, take the derivative kind of problems. So why don't you, again, take a few minutes, grind through these guys. We'll do them together in a few minutes and talk through the result. And does this feel okay, guys? Helpful? Getting our, math juices flowing again? And I would hope this last kind of problem is the one you guys feel the most comfortable with. Is why I kind of started abstractly, because I feel like that's the stuff we struggle the most with, is the conceptual pieces where it's just I'm still kind of getting a handle on the definitions and the symbols and the notation and what stuff means the same and how do I check for stuff. And so I wanted to make sure I did a couple more examples of that kind of thing before the test, because you might see something similar, you know, encounter some piecewise functions and being asked about differentiability, or use some of these things you get from differentiability to answer questions. If you're given that the function is differentiable, what else does that get you? David.
What's the derivative of x e?
Product rule.
I know e of x is by itself. Wouldn't it be x? You separate it.
Be x times the derivative of e to the x plus e to the x times the derivative of x.
Oh, so you do another.
You have to do a product rule inside of your quotient rule. 100%. Should you expect to see that on your test? Yes. I promise you will see a nested derivative problem where you have the product rule nested inside of a quotient rule or a quotient rule nested inside of a product rule. Probably the first one because we don't have enough material or derivative problems to get a quotient rule nested inside of a product rule yet. Because the only two things we can differentiate right now are e to the x's and polynomials. So I can't really. I mean, I guess I could. I could do something like that.
Do you want us to like multiply everything through and simplify for answers, or?
I gave the simplified answer because, again, these things could appear as multiple choice questions. If it is a free response question, you can stop when the calculus is done. Like when the derivatives are over, you don't need to simplify everything down. But if it's a multiple choice question, obviously you got to keep going until you can tell which answer is the one you need, right? Sammy?
So the calculus is done, just means you load everything into the product rule?
Means that you've taken all the derivatives. So like anytime there's like a ddx to do, you've done it, right? So like, you know, for the, you know what I mean? Okay. So if you've done all the derivative rules you can, calculus is done. The only thing left to do would be to like do algebra to simplify. You don't have to do the algebra to simplify. You can stop on a free response question. How do you guys feel after doing some of this stuff? Is this helpful? Go over B? Mm-hmm. So, to do this, we have to do the derivative of the top times the bottom minus the bottom times the derivative of the top, or I'm sorry, the top times the derivative of the bottom all over the bottom squared. So far, so good, Adrian? Okay. So if I'm doing this derivative, the derivative of 3x is just 3. But the derivative of x e to the x requires a product rule because it's the product of two functions. So I'm going to have negative x times the derivative of e to the x minus e to the x times the derivative of x. and the derivative of 1 minus x, the derivative of 1 is 0, and the derivative of x is negative 1. Adrian, so far so good? Okay. And then the derivative of e to the x is just e to the x, and the derivative of x is 1. At this point, you could, if it was a free response question, you could say you're finished. All the calculus has been completed. If I FOIL this out, I'd have this. Let's see, this guy, and oops. Oh, that should be a plus, right? Oh no. Oh, there he is. Okay. It's like there's those are gone, and then those are gone. And then I have that guy. Does that feel good? Okay. So again, the key here is just making sure you're going slow and being careful, right? To just like, don't try to do too much in your head all in one step. Like, write a couple of lines. It really will help. But make sure you're going slow and being careful when you're doing your work, because it's easy to kind of get lost inside of one of these problems where there's, you know, like a couple layers that you have to sift through. Does that make sense? Ideally, none of the single derivatives are that difficult to do, but like when you have like these layers to peel back, making sure you're going one at a time and not trying to do like all of the layers all at once, I think is really important, especially when you're really pretty new to this kind of thing, right? You know, like I made sure when I did this, I did the quotient rule one step. I did the next layer of derivatives in one step. I did the product rule inside of that derivative layer as a third step, where like I just tried to go like one thing at a time and not do too much in one step, because it's easy to get turned around and miss something, or do something the wrong way. Now, did you guys have other questions on things that you saw while you were reviewing from the multiple choice or the free responses or homeworks? Or before I move on to new things, I figure I'll give you guys one more chance if there's anything else that you saw while you were reviewing that you wanted to talk about. I would take some time here and do that as well if anybody has anything they wanted to ask about. Again, the multiple choice and the free responses, I posted the keys along with them, but there's sometimes not a lot of explanation in those. And if you're like, okay, I just don't see where this answer is coming from, can we talk through it? I'm happy to do that kind of thing and take a few minutes now to do that. Peyton?
Did you do 22?
22 on the multiple choice. Okay. I'm just going to do this just off to the side on this packet. So it says, suppose that f is an odd function. That is that f of negative x equals negative f of x. Suppose that f prime of x naught exists. Which of the following must also be equal to f prime of negative x? Okay, so let's think about this as a, let's think about a specific example. So Peyton, can you think of a specific odd polynomial or odd function for me? I gave it away there. Yeah, let's just pick x cubed, right? Like that's a pretty canonical. So the derivative of x cubed should be 3x squared, right? So if I did f of negative x naught, that's going to just be negative x naught cubed. But if I do f prime of negative x naught, that's just going to be 3x naught squared, but it'll be positive this time, right? So what it looks like to me is that when I take the derivative, it kind of ruins the odd part of my function, and what I'm going to be left is an even. So like what I'm trying to see here is like d dx odd equals even, right? So if I had up here that for my odd I have something like this, for even then, oops, I'd have that, right? That's the definition of an even function. So I'd be expecting A. And again, for a problem like this, if you're not really sure, I think the easiest way to kind of build up some intuition is to just like, well, let's look at a specific example of an odd function, right? And hopefully you'd have remembered that like any monomial with an odd power is an odd function. And if you remembered that, then easy to generate an example to kind of figure out what's going on. Does that feel okay, Peyton?
Yeah.
Yep.
Is it for f and then instead of x and then oh, okay.
Yep. That's okay. Happy to zoom in.
What is that? What is it? X to 0. What is that?
That's all that means is a specific value of x, right? Like there's just some value of x, like a number, some constant. They could have easily done -2 there or something. It would have been fine, but I think they just being arbitrary, which again, like getting used to that is part of what we're trying to do with the multiple choice questions, is to just get used to the abstractness of like looking at that, not being confused by the x naught, just going, just a number is all that means. So f of some number negative is just negative f of that number. Peyton, I can see you're ready for another one. Go ahead.
Can you just do the last one, 16?
I hope so. It's awful embarrassing when I can't. We got. Okay. Okay. So it says the figure above shows the graph of f. Which of the following is its greatest value? So we have f of a, f prime of a, f prime of c, f of d minus f of c, and then f of b minus f of a over b minus a. So let's start eliminating the things that we know it can't be. F of a is a negative value, right? Can't be that because f prime of a, that's a positive value. And that's actually a pretty steep slope there, right? Everybody agree with that? That that's fairly close to vertical. So I'll say that that's much greater than 0. F prime of c is this slope. That's equal to 0. Well, that doesn't beat f prime of a. Everybody agree with that? F of d minus f of c, well, that is just like that gap, right? I mean, that's just like, I'll put a single greater than 0, but that's definitely not bigger than whatever the slope is for, or the slope is at a. Everybody agree? And the last one is f of b minus f of a over b minus a. What is that? Yeah, it's this slope, right? Everybody agree? Which is steeper? The red slope or the orange slope? The red one, for sure, right? Everybody agree? Easy to tell because this slope should be less. This is like the average of those two slopes. If I'm taking a bigger value and averaging it with a lesser value, the result should be less than the big one, right? So it should be B. Does that make sense as to how I kind of reason that out? So again, I'm just looking at, like using slopes and reading the graph that know that, that what I'm talking about for f of a is the y coordinate and f prime of a is the slope of f at a, and just kind of eyeballing it a little bit. But that's a good one, right? If you're given some graphs with no y coordinates marked anywhere, can you figure out like what's the biggest value, or something's positive or negative, or that's a nice skill to have, and certainly something I would expect to see in a multiple choice question is something similar to this, where you're given like a graph or graphs without any y coordinates on them and asked to say something about like some function that's defined as one of the graphs, or like a multiple of one of the graphs, like 3f of x minus 5 or something, or f of x times g of x, or something to that sort. But you kind of use the same idea, right? Just kind of eyeballing and deciding if things are positive, negative, or 0 is usually enough, or how positive or negative or 0 it is, and just comparing it. Okay. How do you feel okay? Well, I'm looking at the time here, and rather than starting anything new, which seems kind of pointless with 20 minutes left, I'm just going to kind of skim through stuff here and look at some other examples from these free responses or multiple choices. Sound okay to you guys? Okay. I don't know that anybody's asked about these or had any real time to look at them, but let's do that. So here you're given a graph of f and a table of values of f, and we're told that the graph has a horizontal tangent line at 2. It's concave up from 0 to 5 and linear for greater than 5. It says approximate the value of f prime of 4.5. using the data from the table, show the computations that lead to that. So do I have enough information to calculate the instantaneous rate of change for f of 4 or at 4.5? No, right? What will I use instead as a proxy? I'm going to use an average rate of change, which just means that I'm going to be using a slope. What slope would I want to do? I'm just going to go from 4 to 5 because I'd expect the slope at 4.5 to be a reasonably close to the slope from 4 to 5. Everybody's okay with that? Yes. Sure. It's okay. Oh, yeah. Right. I don't want to do that. Very good. So let's not do that. Yeah. I guess I could use 4 there. And I think I'd still be okay. But yeah, let's not do that. Well done, Vinny. Or sorry, you're Anthony. Wrong Tartaglio. So I guess we'll just do 4.5 to 4. And that's good enough. Is everybody okay there? You see what Vinny was saying? I'm sorry, Anthony was saying? I did it again. Brain is broken today. That I don't want to use 5 because the data for 5 is at 1. And it says using the data or using the table. So I don't want to read the graph and use 4 from F, although it's not incorrect to do that. It just doesn't follow the directions. Everybody's okay with that? That whenever it asks us to approximate a derivative, probably all we're going to be doing is using a slope. It says, is there a value of x from 0 to 5 such that the limit as h approaches 0 of f of x plus h minus f of x all over h is equal to 0? Give a reason for your answer. When you see this, well, I should say, when you see this, what is this? It's the derivative of f, right? Which is the same as slope of a tangent line. I'm told I have a horizontal tangent line at so my answer would just be at x equals 2. That derivative should be 0 because there's a horizontal tangent line given to me there, right? Peyton?
For A, is like doing that kind of what you meant by using the IVT hero in this chapter? Because you have to like.
Not exactly. Yeah, I think there's a question coming where that actually is an IVT question. I don't remember if it's in this one or a different one, but there's definitely one coming. And then it says, for each of the following limits, find the value or explain why the value does not exist. So if you look at these, what do these all look like? Definition of a derivative, right? So this one, because there's no left or right hand limit, is just the derivative at 5, right? What's happening at 5? Discontinuity, right? What does that say about the derivative? Does not exist. Okay? The right-hand limit, or the right-hand derivative, is going to be this slope. Everybody's okay there? what's that slope? It looks like negative 1/4, right? We went positive 1/4. We go 4 over and 1 up. Everybody agree? So that's this one. And this one is going to be, we'll just do an approximation here, right? Because we can't find that slope exactly. What should I use to make that approximation? I'm going to use this and then that point. Everybody's okay there? And that's really probably as good as I can do there. You guys feel good? Let me scroll down and find well, maybe there isn't an IVT question in here. These are both basically the same question though, right? I guess Peyton, what I would say is that like the only thing that would come up is here we're told that like G is differentiable, which would tell me that like G is continuous. And if I needed to do IVT with G, then I have like that part of the IVT covered. I have the continuity covered for it. If I want to show F is continuous, I have that G is continuous, right? And I have that 48 plus t squared minus t cubed over 12 is continuous, because that's polynomial. So all I need to do is check at 6, right? Because this is 6 to 12, and this is 0 to 6. Okay, there. So I can just check to see if 48, and just plugging 6's into each satisfies this. Now I'd be a little bit more careful with my notation, but that's essentially all I need to do. Just to make sure that those two match up. And they will. Does that feel okay? So again, there I used differentiability to get continuity to show that this was continuous across a domain, right? To do that, I have to do chunk, and then meeting for a piecewise. Oh no, I thought those are pretty good questions. Let's scroll through these MCQs. There's probably some good conceptual ones in here. Again, average rate of change means slope. Let's look at 5. let f of be the function defined by f of x equals the square root of the absolute value of x minus 2. Which of the following statements is true? Continuous but not differentiable at 2, differentiable at 2, not continuous at 2, that the limit as f of x, or as x approaches 2 of f of x is not 0, and x equals 2 is a vertical asymptote for the graph of f. Which ones are crazy? Which ones can we cross off right away? Who said E? Good job, Anthony, right? Like, what's the only functions we know that have vertical asymptotes? Would be logarithm or rational function, right? Nothing else is, or I guess a tangent or something like that. But like a polynomial, even if you slap a square root on it in absolute, you're not going to get a vertical asymptote out of that thing because there's no divide by 0 possibility. Everybody good? Okay. Is this thing, what else is crazy town?
I didn't see the.
Well, C should be crazy, right? Is x minus 2 continuous? Yeah. If I take the absolute value of it, what changes? Well, it's just all above the y-axis now, right? What does it mean if it's all above the y-axis? The y value is positive. If I square root that y value, what's going to happen? Still returns a value for me, right? Can I have a discontinuity on that? The only thing that can create a discontinuity here is the square root. Am I ever square rooting a negative? No, because I'm square rooting an absolute value, right? So like, I think that's crazy town. Can't have a discontinuity there. So if it's continuous, well, I guess that's okay. So let's keep thinking here. We've eliminated 2 choices. That's great. What's this thing going to look like underneath this? What was this thing going to look like when we just had the absolute value? It's going to look like some kind of a V, right? Where's the point of the V going to be at? 2. Very good. If I square root that, then, is that going to change that it's a corner? No, it'll look a little bit more cuspy or something. It'll look like, you know, like that. But it's still going to have the corner there, right? That looks like probably my best bet. We have continuity but not differentiability. We're pretty positive we have a corner at 2. I would cross that out. And the limit at 2 is not 0. That should be what the limit is for f, right? Because this should be the x-axis. Right? If I'm heading to the left or to the right, should be A. You guys cool with how we kind of did that? Even with no calculator to look at the graph, we can still kind of point out that there's going to be a corner at 2, hopefully. 6 is very much what we just did. Oh, here's a good one. Oh, no, I don't want that one. Let's do this one. This is a good one. 13. The graphs of 2 differentiable functions f and g are shown. P of x is the product of f of x and g of x. which the following statements about p of -2 are true? So if I go and I look at f of -2 is 0. F prime of -2 is greater than 0. G of -2 is negative. And G prime of -2 is positive. So if I have 0 times a positive, that's 0. And then I have a positive times a negative, that's negative. So I should have that, that's a negative value. Is everybody okay with how we kind of did that, even though there's no numbers involved? I just kind of looked at what was going on. It's a nice problem because it really forces you to relate slopes and derivatives together, that's what you're using the graph, is just estimating a slope from it. And a number doesn't really matter in a question like this, it just mattered if it was positive, negative, or 0. Let's look at some more. Oh, here's a nice one, 19. So it says, let f be the function given below. What are all the values of a and b for which f is differentiable at x equals 1? So we need continuity, which means that when I plug 1 squared in, the left and the right pieces equal. And then for differentiability, the left and rights have to be equal. So I use the first one to solve for A. I use differentiability to solve for A and get that answer and plug it into the equation for continuity to solve for B. Does that make sense, guys? This is the same kind of problem here, 21 as 19. You'd approach it the same way. We did 22. Anyway, it feels like we're out of time here. If you guys see anything over the next day or two while you're looking things over, feel free to stop in and try to catch me during community time or whatever. I'm happy to meet with you and look at what's going on and talk you through things, or if you have a question about something, or if you're just like, hey, I don't understand how to do this, or can I do something on the board and just have you give me feedback or whatever, feel free. Come on in, stop by, say hi. Happy to work with you. Okay? Good luck studying, guys.